Hello, in this video we're going to be going over some of the problems from Thermo Practice number 4. So let's get right to it. So if you look at problem number 1 is asking about entropy, and the symbol that we use for entropy is S. And we rarely talk about the value of entropy for a given object. We're focused on the change in entropy, so we use the symbol delta for change, and we're thinking about, during the course of a reaction or some other process, is entropy increasing or decreasing? And entropy is a measure of the disorder of a system. So let's look at some of these scenarios and think about whether entropy is increasing or decreasing. So in A, we're going from a liquid to a gas. So if you imagine what's happening here, liquids are relatively close together and organized, whereas gases are very spread out and moving around randomly. There's a lot more disorder in a gas than a liquid. So going from liquid to gas is going to cause an increase in disorder. So we could either write increase, or we could say, it's a positive delta S for that scenario. If you look at problem number 2, you've got 2 moles of a gas coming together to form 1 mole of something. So two things that were before had been kind of freely floating around, all disorganized. Now they're locked together and they're kind of more stuck in place, so they're more organized. So it's going to be a negative delta S. There is a decrease in disorder. So this happens because there's a decrease in the number of moles. Up here, let's go back to part A. The reason why there's an increase here is because it went from a liquid to a gas. So the main things you're looking for is there a phase change, or is there a change in the number of moles before and after a chemical reaction? So if we look at C, we go from 1, 2, 3, 4 moles of gas beforehand to only 2 moles of gas afterwards. So this is also going to be a decrease in entropy because we're going from 4 moles to 2 moles. So there's less disorder there. If you're looking at D, you go from 26 moles of gas floating around to 34 moles of gas. So there is a increase in entropy happening in D. And in E, we've got 2 things happening. One, we've got 2 moles turning into 1 mole, and we also have a gas turning into solid. Both of those things will produce a decrease in entropy. And then F, we are looking at an increase in entropy here. And again, we've got 2 things happening. We've got 2 moles of reactant turning into 3 moles of product, and we also have a liquid turning into a gas. So make sure you pay attention to the subscripts, the states of matter there. All right, looking at problem number 2, again, is the change in entropy positive or negative? So A is going to be positive. It looks like maybe that's going from a solid to a liquid or something like that. B, it looks like they're getting more, mixed together, so that's going to be positive. And D is going to be negative. They're getting stuck together, becoming more organized. They're less free to move around. Okay, so when things are more freely moving around, more mixed up, then you have more entropy. Okay, so taking a look at 3, this brings us to some problems in which we can use the equations from your equation sheet. So I'm going to flip over here to OneNote, and if you look on your equation sheet under the Thermochem section, there are 5 equations here, which can be helpful when we're doing thermochemistry. So on this problem, we're going to be looking at this equation right here with delta S. Okay, so it looks very similar to the equation we're familiar with finding delta H using heat to formation. So you would be given a table of values showing the standard entropy of things, and you take the entropy of the products minus the entropy of the reactants. Just like with heat to formation, we do products minus reactants. It looks like we do the same thing right over here with delta G as well. So these equations on your equation sheet, you don't need to memorize them. So let's go through one of these together. So if you look at A, and we're trying to find delta S, it is the sum of the S of the products minus the sum of the S values of the reactants. Make this pen a little bit thinner here. So if you're looking at problem A, we've got 2 H2 gases. It's important to pay attention to states of matter. because the entropy of, gaseous hydrogen is going to be different for than solid or liquid. And so these are our products. Then we're going to subtract the reactants, which is 2 liquid waters there. So we're going to look over here at our table. It looks like H2 is right here. So 2 times, 130.6 plus our oxygen is 205 minus 2 times the liquid water. So you got to make sure you use the right value. And when you plug that in for A, you should end up with positive 327 joules per mole Kelvin. I'm only going to walk through one of these because the other examples are all the same, just with plugging in different numbers. So you want to be using this equation, products minus reactants. And when you do this, let me write down the delta. I'll actually write down the numbers you should get here. So you should be getting positive 327 for A, and then you should get negative 1,087 for B, and positive 89, and then negative 387. And notice the units here are joules per mole Kelvin. This will be important later on, whereas delta H's are usually given in kilojoules or kilojoules per mole. So remember, a kilojoule is 1,000 joules. So let's get to some explaining. Problem number 4. Why does 3D have a negative delta S and 3C has a positive delta S? So let's look what's going on with 3D and 3C. They look very similar, these two equations. The only difference here is in C, everything's a gas, right? Whereas in D, one of these is a liquid. And liquids have less entropy, than gases, because liquids are more orderly, so they are less disorderly. It's kind of weird with the double negative there. So liquids have less entropy, so the change in entropy for D is going to be negative because you have all gases on your reactant side, but on the product side, some of them are liquids. So that's going to cause a decrease in disorder. So that's going to give you a negative S value. Whereas let's not forget C. Let's look at C. C, you have 5 moles of gas on the left, and you have 6 moles of gas on the right. So everything's a gas, and you're increasing the moles, so that gives you a positive delta S value there. So looking at number 5, which of the reactions will be thermodynamically favored at all temperatures? So we have to, when we're thinking about who's thermodynamically favored, we are looking at this equation. Let's go back to our equation sheet. We're looking at this equation right here, and we're thinking about the value of delta G. So if you have a negative delta G, that means you are thermodynamically favorable. Okay, and that means that the reaction is going to occur spontaneously. So if we think about this equation here, so delta G equals delta H minus T delta S. In order for it to be thermodynamically favored at all temperature, that means that no matter what these values are, no matter what the temperature value is, the delta G will always be negative. That's what it means to always be thermodynamically favorable. So if we think about sign here, in order for G to be negative, guaranteed, that would happen if delta H were negative and delta S were positive. Because in this case, you'd have a negative minus a positive. That's always going to give you a negative number, no matter what the temperature is. So if we have a negative delta H and a positive delta S, then it's always thermodynamically favorable. So if you look up, so let's look back here and see if any of these fit this scenario. So a negative H and a positive S, that looks like 3C is always thermodynamically favorable, okay? Because 3C has a negative H and a positive S value. Okay, so calculate delta G for the other 3 reactions, 3A, B, and C. And delta G, with that little symbol there, so G naught, that means standard conditions, which is going to be 298 Kelvin, and it's not really relevant at this point, but you could also note that if you have a gas, it's 1 atmosphere of pressure, or if it's a solution, it's 1 molar. Those values aren't going to be useful to us right now, but they will come up later. So calculating delta G, let's just work through this for one example. So 3a, we're going to be using this equation right here. Let's go back to our equation sheet. So if we're finding delta G, we've got 2 equations for finding delta G. There's this equation, which looks like our heats of formation equation, or there's this bottom one here. And so which equation we use depends on what we're given. If we're given a bunch of G values, then we could use this equation right here. If we're given some information about H and S and T, then we'd use this equation down here on the bottom. And that's the one we're going to use right now. So here's our equation, and here's where it is important to pay attention to units. Okay, and you will see why in a minute. So for 3a, our delta H value is, let me scroll out here a little bit so we can see it better. No, it's not letting me scroll. Okay, so for 3a, our delta H value is positive 572, and that is positive 572, and the value is given in kilojoules per mole, okay, and the temperature is 298 Kelvin. This temperature must be in Kelvin. And if you look at our S value, let me write it right here. Our S value is 327 joules per mole Kelvin. Okay, that was the S value. Let's confirm and make sure I had that right. Yep. Okay. What we should be noticing here, hopefully, is that H is in kilojoules, but S is in joules. So if we're trying to add things together, we can't add things or subtract things if they're in different units. So I need to make sure I convert my S value into kilojoules in order to be able to subtract it from my H value. So 1 kilojoule is 1,000 joules. That's what kilo means. So in order to convert joules to kilojoules, I'm going to divide it by 1,000, and my S value is going to turn into 0.327 kilojoules per mole Kelvin. So if I plug this in here, 0.327 kilojoules per mole Kelvin. So you see, this is how I know my temperature needs to be in Kelvin, because that's showing up in my S value there. And everything else cancels out, and I'm left with 2 values that are both in kilojoules per mole. So when I go through and I plug this all into my calculator, I end up with 475 kilojoules per mole. Let's see, is my, I had the sign wrong. Whoops, because this is supposed to be positive. Sorry, this is a positive H value. Okay, so I end up with a positive value here at the end. So it is very important that you need to convert your delta S values to kilojoules first. Okay, this is a big rule of thumb with this calculation, and make sure with the temperature you need to use Kelvin. And you need to be careful with sign, like I started out having my sign backwards, so you need to be careful with that. So that is the answer for 3A, and when you go through and you solve for 3B, you're going to do the same process. 3B, you should get negative 2,973. And for 3D, you get negative 1423 kilojoules per mole. So 7 says which of the processes from 6 are thermodynamically favorable, and anything that has a negative delta G value is thermodynamically favorable. So that means that processes B and D are favorable. A is not, because A has a positive delta G value. So if someone's asking you if something's favorable or spontaneous, or like what would make something more favorable or spontaneous, they're just asking they're just asking about the sign of G. That's all we're really talking about here. And if you're looking at 3A, at what temperature does this reaction become thermodynamically favored? So let's see, my values for, I have this written down somewhere. So for 3A, my values for delta H were positive 572 kilojoules. and delta S was 327 joules per mole Kelvin. And the key thing, if I think about what we're being asked here, is if the delta G is negative, then it is favorable. If delta G is positive, then it is unfavorable. So the question is asking us, at what point does this reaction go from being unfavorable to favorable? So basically, what is that like tipping point? What is just in between G being positive and G being negative? And the answer is G being 0. That's what's exactly in between it being positive or negative, right? So when G is 0, that's kind of the tipping point between making a certain process become favorable or not favorable. So, in reaction 3A, we know that this one is sometimes favorable and sometimes not. And so we want to figure out at what temperature does it switch from being favorable to not favorable. So we're going to use this equation, delta G equals delta T minus T delta S, and we're going to solve for that point, for this tipping point right here, the point at which G is 0, okay, where it switches from being favorable to unfavorable. And delta H is positive 572 kilojoules per mole. We don't know temperature, that's what we're trying to solve for. But S is 0.327 kilojoules per mole Kelvin. And if you go through and you rearrange this, you end up with 572 equals 0.327 times T, and when you solve for T, you end up with 1750 Kelvin being your answer there. Okay, so those are questions